All right, here's a couple problems that we're going to look at regarding graphing a function if we know its derivative graph, all right? So here we're looking at a graph of f prime, and so we want to keep in mind here that this is f prime, the derivative of f, and we want to graph f of x, okay? So we want to graph f of x and f prime of x, or f double prime, all right? I want to explain the characteristics of what each graph looks like, concavity, increasing, decreasing, all that jazz. And we're going to use a set of axes for all three, or we're going to separate the graphs. So let's separate them here. We'll use this second graph over here for the new ones, all right? Sometimes it gets a little confusing when we do it on the same one there. So let's look at this derivative graph, and we can find a few things out here, okay? First of all, we can find out where the derivative is 0, okay? And so we know f prime of x is 0 at x equals -2, 1, and 3. Those are possible minimums and maximums, right? And they are minimums and maximums because the derivative is changing. Over here it's negative. On this interval right here, it is positive, the derivative is. And down here for this interval, from 1 to 3, we have a negative derivative. And for 3 to infinity, we've got a positive, okay? So that's the change in the derivative sign. The derivative is the slope of our function. And so since the slope is changing, these are minimums and maximums, all right? So another useful thing is just to kind of make rough sketches here, all right, as we do this kind of thing. So -2, 1, and 3, we know those are special points so far, okay? And so we know our graph is coming down, our graph of f, that is. It's coming down to somewhere on -2, and it's going up because all of this is positive here. So that graph is going up. Between -1 and 3, we're going down. And from 3 to infinity, we're going up. All right? So we know we have a minimum at x equals -2. And also at x equals 3. We have maximums at x equals 1, it looks like, so right over here. Okay? All right, so we've got some quick information there. We know when the derivative is, well, the slope of the derivative graph is our second derivative, okay? And so the slope of this graph is 0. That'd be the tangent line. And it looks like about 0.75. How about we call that 0.75? So let's jot that down here. Maybe different color. So let's talk about f double prime. That's the slope of the f prime graph, the derivative graph. So that's 0 at about x, that's my at there. X equals what, 0.75, and over here, what about 2.1? All right, this is an approximation game here, all right? Going to get the best graph we can, okay? So those are our inflection points, our possible inflection points, okay? Possible inflection values at x equals 0.75 negative, that's a negative, right? And a 2.1-ish, okay? All right, so that's good. We know that it's going to be concave up. Let's talk about concavity here. Okay, so we know f is going to be concave up is concave up. Okay, when do we find concave up? Well, we find concave up when the derivative is increasing. So when we're talking about f, okay, when the derivative, if this is a graph of f of x, okay, when when the tangent lines are getting steeper and steeper and steeper, that is when we have concave up. That's the definition of concave up. So we want to know, when is the derivative increasing? Well, the derivative is increasing. Let's see here. Let's look at the graph. It's increasing on this spot right here from 0 to 0.75. So the derivative is increasing. That means that it's concave up from 0 to negative 0.75. Okay? It's also increasing over here. And let's call that from 2.1. How about that? To infinity. All right, so there's concave up. And let's see, gonna run out of room a bit here. We got more. Okay, F is concave down. Is also known as that. Concave down. That should be two words in between those two things. So negative 0.75 to 2.1. All right. So with that, I think we can get a pretty good graph here. Okay. Now, we don't know any specific points for f of x. And well, you know, before we do that, one more thing here. We kind of wrote this, but we didn't formally write it down. We just did the little graph. Increasing and decreasing, we talked about that. Decreasing from negative infinity to negative 2. Increasing from negative 2 to 1. Decreasing from 1 to 3. And increasing from 3 to infinity. All right? All right, so we're graphing some possible graphs here, all right? Since we don't know an initial condition, maybe we'll assume it goes through 0, 0. All right? So we know from 0, 0, we know we're decreasing down to 2.1. So somewhere down here at 2.1, and an x value of 2.1, we're going to have a minimum. Okay, we have a point of inflection at, I lied. Hold on a second. Let's back up. Our minimum is at 3. Our point of inflection is at 2.1. Okay? All right, so that means it's gonna change to concave up from here. Now, by the way, that gives us a little bit of a clue that, this is, let's see, we have a maximum at 1, all right? So, yeah. Somewhere up here we got a maximum, all right? So we're going to be concave down. How about that? All right, we're going to come through maybe at about 1. We know we have another inflection point somewhere right about here at 0.75. So it's concave down there. Whoops. And then it's going to be concave up. We have another minimum down here at negative 2 somewhere. So we're going to turn around at negative 2 and head back up. So there is a graph for f of x. End behavior is going up. That's important. And, the height of the mins and the max, we don't know, but should be something like this. And in reality, it's probably not as rounded as I made it here. So, all right, so there's f prime of x. Nope, sorry, f of x. And since we don't have another grid here for us to graph another f double prime, let's go and put f double prime on the same graph as f prime. Let's try that. Okay. So the second derivative, we know that the tangent line is 0 at this value 0.75. The tangent line is 0 here. Okay. As we look at this graph here, keep in mind that we are finding the second derivative, and the second derivative is a derivative of the derivative, all right? So that's what the second derivative is. So we're thinking tangent lines here. All the tangent lines here on this part are positive because that's increasing. So the derivative, the tangent lines of this curve are positive there, all right? From 2 to infinity, these all have positive tangent lines, positive slope, that is. So it's going up. In between here, we have some negative. Okay, all the tangent lines here are going down. So those are all tangent lines have a negative slope. So we're going to have a negative in here. Negative slope, so we're going to scoop down here like this. All right, and there is f double prime. The derivative of the derivative. All right, so some things that kind of confirm that we're on the right track here are our derivative graph, our f prime graph, our first derivative, looks like a cubic, third degree. So when you take the derivative of a third degree, you get a second degree, something like a parabola, all right? And since the derivative is third degree, a cubic, that tells us that our original function was probably a fourth degree. Using our power rule, when we go from x to the fourth, take the derivative, we get x cubed. When we take the derivative of x cubed, you get x squared, and that's a parabola. So those shapes kind of reinforce that we're on the right track. And we know this is x to the fourth because it's going up and up, and because it has 4 zeros, 3 extremas, so it looks like a good x to the fourth. Not the best drawing, but that's the idea. So those are the key features you need to have. You might move this up or down, all right? And that all depends on the initial conditions, which we were not given. So we'll leave it at that, and there you have it. Let's look at the next one real quick. The question here is that these functions are related by derivatives. Determine which one is f of x, which one's f prime of x, which one is f double prime. All right, the first derivative, second derivative, third derivative. Okay, so you can kind of tell these are some sine waves going on here, all right? This guy right here is some other, so it's something else, a sine wave with something else added on, okay? But don't worry too much about identifying what the function is. Let's think about the derivatives, okay? So we know here, let's look at this dotted line here, this dotted one right here, all right? Look at where it has tangents that are zeros, okay? So the zero tangents line up with this, okay? So here we have a tangent line, and the black line here has a 0. That's good. The black line 0 there. All right. So all of the places where this dotted line or dashed line has horizontal tangent lines, the black line is a 0. So we definitely know that this black line is the derivative of this dashed line. Okay. Now the question is, where does this dotted one belong in? So let's say this leads to this. All right. So we'll find out here in a second if the dashed line is f of x or f prime. So let's take a look at this dotted line up here. So this dotted line does not have any, oh, there's my lightsaber pointer, like it. Okay, so this dotted line there doesn't have any minimums or maximums. It almost does there, but it's not. It's always increasing, okay? So the derivatives are always positive. We never have derivatives that are going down. So if I want to take the derivative of this function, I'm going to get a graph that is always in the positive. Where do we have a graph that's always in the positive? That's got to be this dashed line. The values of the dashed line are always positive. So the values of the dashed line are the derivative of this. So the derivative of the dot is the dashed. The derivative of the dashed is the solid. Okay? So I'm going to put these arrows like this. Okay? So let's get rid of that one. So this dotted line goes to the dashed line goes to the solid line. So that means that this is f of x. The dashed line is f prime of x. and the solid line is f of x. All right? So, and that comes from f of x is always increasing. Okay? Since it's always increasing, then we could say that so f prime of x is all positive. And that's how we got that one. Okay? And then f prime of x, the dotted line, has 0 derivatives. Dx derivative of f prime of x, I guess we could say, equals 0 at these values here, at the zeros of the solid line. That's how we got that line. Okay, so the solid line, oops, I think I marked this wrong. Goodness gracious. This is f double prime. Because that's the derivative of the derivative. Okay, so the solid line there has got to be f double prime. Okay, all right. That's the idea.